Okay, so now we are going to see how we can get the information about the constants from the tables of CV and CP, of course. Type this table that we're going to be using is table B2. Let me open it for you from the textbook um, just to make it easy for me and for you to look at the whole table and be more familiar with it. It's table B2, which is this table in the textbook. You see this table is not, I just have here in the slides just a screenshot of the first part of the table. It's not the whole table. So the table is 1, 2, 3 pages. It's almost three pages, yes. So there are things that I want to, I put it in full screen mode to make it more clearer. So I'll be discussing it here because I want to have a more clear view of the full table. Fine. If we look at the table, you'd see that it says heat capacitors, and it says form 1 and form 2. It says CP in kilojoules per mole Celsius or kilojoule per mole Kelvin. And we have two equations here. So this is just to before we start, there is not one uniformal or universal formula of the CP equation. The equation that we know, which is the most famous equation, is the first one, which is form 1. There are some cases, and we will see this shortly, that we have another equation for. Both equations are polynomial equations, so they are going to be very easy when it comes to the integration. For the integration, it's adding 1 to the power and dividing by the new power. So it's going to be AT plus BT squared over 2 plus CT power 3 over 3 plus DT power 4 over 4. So it's very simple and straightforward integration. Here's the only difference in this equation. It's going to be CT power minus 1 over minus 1. This is the only difference. So regarding the integration, it's not a problem. So this is the equation. It's important to pay attention to the units. This is kilojoules per mole Celsius or per mole Kelvin, and we will understand why we have these two forms of the equations. But the important part of this is that if you calculate the enthalpy from the integration of CPDT, that the output is kilojoules per mole. Because you are multiplying by temperature, so this Celsius will cancel out, so you'll have only kilojoules per mole left. So this is the units of the specific enthalpy that we are calculating is going to be in kilojoules per mole. It's important because there are some other textbooks or some other references that provide constants that will produce enthalpy with different units. And this is important to pay attention to. That this is not the universal units that you will have. These are the units that you get from this table. Okay. So now when we look at the table, you would see here that the first column is the compound. You have acetone, acetylene, air, and so on. And it's clear that the compounds that we have here are arranged by the alphabetically by the name. So we have A, B, C, and so on. So it makes it easy for you to look for what you are looking for. Now for the second column, it's the formula. This is the chemical formula of the compound. Then we have the molecular weight. These are very simple, straightforward things. Now we have the third column where we will start to go into more detail. So it says the state. State, it means that is it the phase, or what is the phase of the compound? Is it liquid? Is it solid? Is it gas? So we'll see here cases that it says it's liquid. There are cases that say it's gas. So L is for liquid, G is for gas, and so on. So you can see there are liquids and gases. But you would expect that the three options are L, G, and S: liquid, gas, and solid. But you'll have here L, G, and C. And if you look for any S, you will not find any S here. They're all L, G, and C. So this liquid is L, G is gas, C, it means that it's a crystalline solid. Means that it's a solid that has crystal structure. It's not amorphous. That's why we have here this shape or this letter C. At the end of the day, it's solid. So this is what you need to be aware of. One thing that you will notice here that the crystal structure, of course, I'm not sure if you're aware of this or not, but the crystal structure depends on the material. There are some materials or solids that take a cubic crystal structure. It's like salt, the table salt that we have, it takes a cubic shape. There are other solids that take rhombic structures. They might take hexagonal structure. They take different crystal structures. You would see here that there is something here for sulfur. It says rhombic, and there is monoclinic. So there are different crystal structures, and the constants are different for the two crystal structures. So this is just to give you an idea of what we mean by this. Anyway, so this is the second column. So we know what is the state. We understand it now. For the form, it refers to the two equations that we have here. We said there are two equations, forms of the equations. So you know which equation you are going to use from this column. It says form 1, form 2. Form 2 is always, at least for this table, is always for solids. So you'd see all the 2's here correspond to crystalline solids for here and for the rest of the table. For liquids and gases, they are all in form number 1. So you need to like pay attention to this column because you want to make sure that you are using the right column. Here you have the temperature units in Celsius or in Kelvin, and this is also important because this is what you are going to be substituting here after integration. Or if you want to calculate Cp directly, this is the units that you're going to be using. So this has to be in Celsius or Kelvin. That's why it's put here in kilojoules per mole Celsius or kilojoules per mole Kelvin, depending on the units of temperatures that you are using. This is also important. Now we'll come to the important part, which is the constants. So you have A, B, C, and D. Some materials here have only A and B. Which means that C and D are zeros. Some contain only A, which means that the rest is zeros. Usually for it's not always, but in I would say 90% or more of the cases, the gases will have the 4 constants, the liquids will have 2, and the solids will have 1. This is kind of trend that you would see. So there are some other exceptions, of course, but this is what you would notice in many cases. The constants for liquids are less than the constants for gases, and the solids have less constants than liquids. So if you have no numbers here, it means that C and D are zeros. So you just use the first 2 terms of the equation. For these 4 columns, you'd see that it's A multiplied by 10 power 3, B multiplied by 10 power 5, C, and so on. So this is a very, very important thing. When you have this in the header of the column, it means that the numbers that you have here are already multiplied by 10 power 3. They are already multiplied by 10 power 3. It doesn't mean that you will multiply them by 10 power 3. It means that the number that you have here, it's the number after multiplying by 10 power 3. So if you want to get the original number, you have to reverse the calculation. So you have to multiply this number by 10 power minus 3, and this by 10 power minus 5, this by 10 power minus 8, and this by 10 power minus 12. So this is important. And to be aware of this, or to confirm this, look at the example that's given here. It says that the Cp for acetone gas, which is the second column here, or the second row here, it says it's 0.07196, which is this number multiplied by 10 power minus 3, and then 20.10, which is this multiplied by 10 power minus 5, and then negative 12.78 multiplied by 10 power minus 8, and then 34.76 multiplied by 10 power minus 12. So you do the opposite. Multiply this by the 10 power minus of this power. And to think of this in a more practical way, if you are calculating the enthalpy for this term, it's going to be multiplied by T power 4, T2 power 4 minus T1 power 4. So the T power 4, if let's say it's 300 degrees Celsius in this case, if this is 300, so it's 300 power 4. So this is going to be 10 power 8. So if you multiply 10 power 8 multiplied by 10 power 12, this is going to be 10 power 20. So this is going to give you like a huge number of enthalpy, which is not logical. So to make it logical, this t power 4 must be multiplied by 10 power minus something to make the numbers equal, or to make the number logical. So again, look at the header, if you, or the example that's given here, to make sure that you are using the right substitutions. And then for the range of units here, it gives you the range where these constants are valid. So it's valid for the range of -30 to -60. So if it's out of the range, then you cannot use these numbers. Finally, there is a note here that the formulas of the gas are strictly applicable at pressures low enough for the ideal gas equation of state to apply. So this applies for the ideal gases, if it's a gas, of course, but this is valid only for low pressures. We said that for liquids and solids, they're not very affected by the pressure, so it's not a big deal. But for the gases, it's a very important note that you don't apply this to very high pressures. This applies for the pressures where the ideal gas equation is valid. So I think this is all what we want to mention here, or to know about this. I just put this highlighted these two rows to compare these two numbers and make sure that you understand it well. Now you will ask a question. This is the table where we have the constants of Cp. What about Cv? You will not find a table like this for Cv. The constants that we know are for the heat capacities at constant pressure. For Cv, we can get a relation between Cv and Cp. For solids and liquids, it's almost the same. So you can use the same constants for Cv and Cp. For ideal gases, we have this very nice relation which says that Cp equals Cv plus R, where R is the universal gas constants, and we know that the R has units, the same units of the heat capacities. We know it's 8.13 joules per mole Kelvin, which is the if you compare it to here, it's kilojoules per mole Kelvin. So it's the same dimensions. I mean dimensions. You have to unify the units, of course. Make sure that the units that you're using are the same. Now, if we are calculating the enthalpy, this is the formula that we will be using. If we want to calculate the internal energy, then use Cv dt, the integration of Cv dt, and Cv equals Cp minus R, according to this relation. And this is how you're going to do the substitution. Of course, here this is I don't know if I mentioned this before or not, but this is an important note before we go through the Cv. The integration of Cp dt is the A plus Bt plus Ct squared plus dt power 3. So we know that this is At plus Bt squared over 2 plus Ct power 3 over 3 plus dt power 4 over 4. The important thing that I want to mention here is that you do the power for each one of the temperatures separately. You don't say T2 minus T1 power 2. The power is not on the bracket. The power is on each one of these two temperatures. This is a very important thing. Okay, so we don't do the power, not raise the power of the bracket. You raise the power of the whole of each one of the two terms separately. This is very important thing. For ideal gases, what we are going to do is we are going to use the same formula, which is Cv equals Cp minus R, and when you substitute, the same thing is what we did before. The only difference is we have minus R here. R is constant, so we can combine A minus R as one term, and this is going to be the only difference. Here we have A, here A minus R. The rest of the terms of the equation are the same. So there's one last thing that is kind of related to this relation for ideal gases. I put the derivation here that you can use to reach this information. We say this is for ideal gas. So we start here with ideal gas, combine it with the relation between H and U in order to get the relation between Cp and Cv. You can go through this. It's very simple and straightforward, and we can check it by yourself. طيب, so I'm going to stop here. Next time I'm going to be solving some examples to make things clearer and to have more practice on the concepts that we mentioned here. So we will continue next time, inshallah. See you then.